Here's your rapid review for Unit 3, Electric Force, Fields, and Potential. The first summary. Objects are made of atoms, which are in turn made of electrons, protons, and neutrons. An excess of electrons will cause an object to be negatively charged, while an excess of protons will create positively charged objects. This chapter or unit focuses on how to deal with electric charges that aren't moving through circuit components, and hence the name electrostatics. An electric field provides a force on a charged particle. So again, this electric field is how we give a reason for the forces that we see. Electric potential, also called voltage, provides energy for a charged particle. Once you know the force or the energy experienced by a particle, Newtonian mechanics can be applied to predict the particle's motion. Here are some key ideas. Electrons and protons are real particles that can move from place to place or transfer from object to object. But the net charge of the system always stays the same. That's conservation of charge. So we saw that with electroscopes and sticky tape. Most objects have the same number of electrons and protons. Only objects with excess protons or electrons have a net charge. Just a reminder that when you're drawing something that's neutral, to include both positive and negative charges. A neutral object doesn't have no charge, it has equal numbers of positive and negative charges. Conductive objects that touch will transfer their charge so they share any excess charge. So we've seen some situations where we'd have an object with charge Q, and then we'd have another object that's initially uncharged. If we touched those two objects together, I touch them together, then after they touch, the charge is going to spread evenly so that each object would have Q over 2. One object can be charged without touching another charged object through a process called induction. So in induction, what we did was we had an electroscope. We brought a charged rod near the electroscope. We grounded the scope at the same time, and what happens is the charges in the rod drive the electrons from the scope down to ground. So when the scope, which began as a neutral object, loses its electrons, it's left with a net positive charge. So charging by induction leaves us with a net positive charge. A neutral object can have an excess of protons on one side and an excess of electrons on the other. This is called polarization or charge imbalance. So we could have a neutral object that has mostly positives on one side and mostly negatives on the other side, and it's neutral, but the charges are imbalanced. Parallel plates produce a uniform electric field between the two oppositely charged plates. This, by the way, is called a capacitor. The positive plate is defined as having high potential. The negative plate is defined as having low potential. So if I sketch a side view of a capacitor, and one plate is positive and one is negative, the positively charged plate is always the high potential plate, and the negatively charged plate is always the low potential plate. By definition, that's just how we define it. The electric field between them is where a force would be exerted on a charged particle. So the electric field is going to point away from the positives and toward the negatives. The electric force on a charged particle is QE, so F equals QE. We'll look at the formulas in a moment. By the way, F and E are both vectors, regardless of what produces the electric field. The electric potential energy of a charged particle is QV. Positive charges are forced in the direction of an electric field. Negative charges are forced in the opposite direction. So this makes sense if you think about where the electric field comes from. If I have two charged plates like this, the electric field is going to point downward. And of course, that electric field tells me the direction of a force on a positively charged object. A positively charged object is going to experience a force going downward, and that's what the field tells us. Positive charges are forced from high to low electric potential. Well, that should make sense based on the diagrams that we've just drawn. Negative charges would be forced from low to high potential. So if I put a negative charge in this capacitor, it's going to experience a force upward, and it's going to go from low potential to high potential, which is kind of weird to think about. Gravity only acts in one direction. Electrostatics can work in two directions. Point charges produce non-uniform electric fields around themselves. So we looked at that too. If I have a point charge that's positive, the electric field is going to radiate out in all directions. Now, when we hand draw these, the field looks kind of like that. We also, though, saw in simulations a vector field where there are little vectors like this showing the strength of the field. Let's see. An electric field is a vector. Electric potential is a scalar. Potential is V, KQ over R for a point charge. And finally, capacitors store both electric charge and electric potential energy. So on the next page, then, we've got our formulas, and I apologize for how this came out. This first one is electric force. So the electric force is, notice in the equation that goes on the equation sheet, they put an absolute value on there because we talked about how a negative would indicate attraction and a positive would indicate repulsion. We simplified this 1 over 4 pi epsilon to be K, so it's K Q1 Q2 over R squared, where R is the distance between the charges. And the name of this is Coulomb's law, force between 2 point charges. The relationship between electric force and the electric field. So here, again, this E is the electric field. The electric field equals the force over the charge. The electric field around a point charge is KQ over R. This top one we can use for a uniform field. Or if you have a point charge and you have a location a little bit away from that point charge, if you know the force and you know the charge, you could use it to find the electric field, but it would only be the electric field at that point because we know when we change R, we would get a different electric field. Let's see, change in electric potential energy is Q times charge times voltage. Electric potential produced by a point charge, again, it's probably easier just to write it with K. The relationship between electric field and electric potential difference. So let's talk about that for just a moment. Let's suppose that I have two charged plates, and let's say that this is the low potential. Let's say this is at 0 volts, and let's say this is the high potential plate. Let's say it's at 12 volts. First of all, I know that I can draw these lines of equipotential, where the potential is equal. And this would, there's like a gradient here. So if the bottom is 4, the center would be 6, this would be 3, this would be 9. So it would have a nice gradient there. Delta V then, from the top to the bottom, is 12. You could do delta V between any 2 points here. You could figure that out. And let's also say, oops, let me change colors. Let's say that we have this distance. Let's say that this distance, just for kicks, is 6 centimeters. Then the strength of the electric field is going to be equal to the change in voltage, which from one end of the capacitor to the other would be 12 volts, actually negative 12 volts, over the distance, which would be 6 centimeters, or 0.06 meters, and that would give me negative 200 volts per meter, which is equivalent to negative 200 newtons per coulomb. Now the negative just indicates that the electric field there is pointing down. Okay, next, potential difference between two charge plates of a capacitor. So ultimately, this thing that I just drew, the capacitor, it's two charged plates. It's got a voltage. The voltage is created by charges. There's positive charge, a net positive charge on the top, net negative charge on the bottom, and delta V equals Q over C. We can also say that the capacitance of that parallel plate capacitor is Q over the voltage. The capacitance is also dependent on the permittivity times the cross-sectional area times D. Here's a formula that combines and gives us the electric field strength between the charged plates of a parallel plate capacitor. And then finally, our last formulas are for the electric potential energy stored in that capacitor. So, and if you think about it for a moment, if we take 1/2 Q times delta V, let's talk about where this comes from for a moment. Q is charge. In coulombs, and V is energy per unit charge. Oh my goodness, I wrote the unit. So again, Q is charge, voltage is energy per unit charge. So you're taking when you multiply those together, you just wind up with energy. Now the 1/2 has to do with the idea that the energy stored changes as a function of the distance, kind of like when you're working with a spring. You may recall working with a spring that if you stretch out a spring, we know that F equals kx, but then the energy stored was 1/2 kx squared. So anyway, just a little more background about where that comes from. Okay, I hope that helps, and let me know if you have any questions.